we had that calculation with the S2. Remember that one? And then I repeated it in the afternoon, but it got a different number. The K value was 50.2, correct? And then we calculated the K value based on our numbers that we determined as 50.19. And then I repeated the calculation in the afternoon, and they got 49.1 rather than a 50.19. And I thought, well, it must have made a calculation error, because if the K value is supposed to be 50.2 and you're getting 49.1, is that close enough, usually? What would you think? Just one second. Let me do this. We're going to be checking in near the end of the lab, so that's kind of closer to 9:30, 10:30, around 11:30 would be the best. If that's okay. Is that okay? Yeah. Okay, thanks. And so, you know, when we do our double check, and the double check comes out as 49.1, right? And it's supposed to be 50.2. Is that close enough? Or would you think maybe something's wrong? Maybe there was a calculation error. Maybe there's something else that came out wrong. Right? And so when you do the double check and the K value that you calculate comes right on the K value it's supposed to be, then you feel pretty confident, right? But in Chem 1B, this is what happens. And this is why I always carry extra digit. At least one extra digit. I used to carry more extra digits, and I thought, one's enough. But maybe one isn't enough extra digits on some. Because what happens is when you do your double check, and the answer comes off wrong, there could be two reasons. One, a calculation error, or two, a round-off error. If it's a round-off error, then the calculation is actually correct. No, it's just rounded off. To determine if it's a calculation error or round-off error, typically you would carry extra digits, even more extra digits than one. You know, most of the time, one extra digit is enough to minimize the round-off error. You know, but the people who tend to round off to the minimum number of sig figs tend to see larger deviations in that, and there, if the deviations are large, you don't know, did I make a calculation mistake or did I just not carry as many digits? And so, you know, repeat that one with the S2, you know, the one we did in class, and see if you get the same numbers. And then see, is your K coming out to, if you follow the procedure that I gave, because I had to repeat the calculation 3 times because I couldn't understand in the afternoon why the numbers were coming out different than the morning. But I didn't punch the numbers in the morning. But repeat those, and if you're getting 49.1, then repeat it again, carrying even more digits to minimize round-off error. Okay? Because we're just carrying one extra digit, then we're allowed, but you know, we're also dropping numbers, and when we drop numbers, we introduce more round-off error. Just to prove to yourself it was round-off error and not a calculation error. Okay. We'll see other examples of this because we're going to do double checks quite frequently. But we were working on that problem yesterday. Let's just continue with that. I don't need this here. And that problem yesterday involved involved a setup that looks like this. Can somebody just tell me what the setup was? So we had the N2O4, right? Plus O2?
No.
Oh, this was 2NO2?
No, what's NO2?
Just
N2O4, right?
Oh, N2O4.
No oxygen.
Oh, no oxygen. Goes to
2NO2.
2NO2s. Oh, that was it. So we set up the ice table, and we see that the perturbed expanding the volume is going to change the concentrations, and the change in concentrations, we calculate Q. Maybe the change in concentrations will not impact, maybe it does. In this case, the change in the concentrations did impact the equilibrium. It's no longer at equilibrium, right? Even though we changed the concentrations both by the same factor. And so that's kind of weird, because if you make it twice as dilute and make both of them twice as dilute, shouldn't it still be at equilibrium? Well, not necessarily, because equilibrium is going to favor the side with when you increase the volume, it's going to favor the side with more moles of gas. And so the initial here, what did we recalculate for the perturbed initial? 1.294.
No, that's the IEQ. I'm sorry. It's 0.3236.
0.3236 molar. And this one?
0.0193.
0.01936 molar. 0.01936 molar.
33.
33.
Yeah.
Right. And then K. C is equal to what?
Oh, 4.61 times 10 to the negative 3.
Times 10 to the negative 3. All right. Now, we already know which way this is going to go, right? Did I already set this up? The rest of the table? Yeah. Yeah. And then I said, okay, why don't you guys finish this? This is quadratic, right? Okay, this is the alternative approach. The alternative approach is this. The way we can visualize equilibrium is like this. Is this favoring the product or favoring the reactant? This is favoring the reactant. So when I see K like this is the way I visualize the equilibrium. The reactant should be favored. And so if I fill this up with water, when I hit the state of dynamic equilibrium, the two water levels are going to be equal like this, right? And water can go either way. I mean, water is free to move, left to right or right to left. And so this is the dynamic part. The water molecules never stop moving, but are the water levels changing? No. And so when I see a K like this, I see that the reactants side are favored in this equilibrium versus the product side. So I should have more reactants than product, right? And so perturbing this, I can perturb it in different ways. So for example, one Le Chatelier's perturbation would be to add more reactant. And so adding more reactant would be the equivalent of adding more water here. If I add more water here, which way is it going to flow? I'm going to get a net flow to the right, and then a new equilibrium is going to be reestablished, right? And so if I add water here, what's going to happen? Well, it depends on your point of reference, but some people will say, yeah, water is going to flow left to right. And so if I add more water here, let's say I'll put it in green here. Will if I add more water to the left, this is a little trick question, but will the water level on the left go down, or will the water level on the left go up? If I add more water on the left. Yeah.
Would it go up and then down?
Well, it's gonna be, yeah, it's gonna go up and down, right? The reason why it's a trick question is because, yeah, it can go up or it can go down depending on your point of reference. If your point of reference is the original equilibrium, then it'll go up. If your point of reference is the perturbed initial, then it'll go down. And so it depends on what you're talking about. It's going to go down after you perturb it, but it's going to be higher than your original equilibrium, so that when the new equilibrium is established, we have to keep track of this. When the new equilibrium is established, you know, the new water level is going to be where? Somewhere around here, say, depending on how much volume we have here. And so this will be the new water level. Let's see. It'll be something like this. And so when we look at it based on the original water level, you know, here versus here, you know, in one sense it's gone down and in another sense it's gone up. And so sometimes people will ask you, you know, what will happen to the amount or what will happen to the concentration of N2O4, you know, after you perturb it. And so then you have to ask yourself, are they asking relative to the perturbed initial? This is the perturbed initial. From the perturbed initial, it should go down. Or are they asking from the original initial? From the original initial, it's going to go up. And so when people are asking about the percent change, you have to go, are they asking for the percent change from the original, or are they asking from the percent change from the perturbed? And so you'll have questions where they ask either, you know. It depends on the context of the question. And so you can't always do it the same way each time because sometimes they'll ask it differently. And so we do the calculations. You know, we do the calculations from the original initial versus the perturbed initial. They're different. And sometimes we calculate the percent change based on that. Is that clear? Good. Well, you know, this is just any old equilibrium. So, you know, I could approach, this is a reversible, right? This is totally reversible. And so let me give you a couple of scenarios here. Let's say there's, this is the concept of resetting initial condition. The concept of resetting initial conditions is like this. Why do this? It's just to simplify the calculation. You know, the more zeros we have, the better. The more zeros we have in the initial condition, the better. So that's one reason. The other reason is limitations of the calculator. You know, how many digits does your calculator usually carry? 8 digits or something, 10 digits, 12 digits, 16 digits. Excel, I think, carries 99 digits or 100 digits or, I don't know, 1,000. But your calculator is going to be limited to how many digits you have. And so what we want to do is we want to reset the initial conditions so that it is closer to equilibrium, so that it is closer to equilibrium, and thus the change will be smaller. Now consider this. This happens sometimes. Let's say your calculator carries 8 digits. Let's say your initial was 1.00 molar. And then we had a minus x, right? And then in this calculation, let's say there was a big change. Let's say the change was 0.999999993 molar. And so we've pretty much lost most of it, or practically all of it. Well, if you do it in Excel, then it's going to punch out 0.999993, and then we're going to be left with, what is it going to be? Well, it's going to be 1.00 minus 0.999. How many nines do I have? 4, 8, 9. 9 nines. And so I'm going to need, how many zeros? I'm going to need 9 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, and then a 7. All right? And so I'm going to be, in fact, I pretty much reacted practically all of it, and I'm just left with a minuscule amount, right, that's left over. And so if you have a fancy calculator, you can calculate this, right? But if you have a calculator that carries only 8 digits, if you have a calculator that only carries 8 digits, then what's your calculator going to do? It's going to round it. It's going to round. 8-digit calculator will round to 8 digits. And so this is going to be rounded to 8 digits, 1.000000. And now when we do the calculation, 1.00 minus 1.000000. What do we end up with? 0 molar. Is 0 molar and 0.907 molar the same thing? Now this is a huge quantity compared to nothing. And so how much reaction occurred? Well, 100%, but really it's 99 point whatever. So we have to watch out for calculator round-off, which introduces another type of error into our calculation. And so sometimes we will reset this. And so let's take a look at an example of resetting this. Yeah. Let me turn this off for a second. Let me make this on. So when we do this like this, let's say I had 100 gallons of water, right? And all 100 gallons were here. 100 gallons of water. And so all 100 gallons were here, and I opened this up. What's going to happen? There's going to be is this going to be a small change or a big change? Big change. Now, what's going to happen is a big change and most of the water is going to be here and less water over here. This is still going to be 100 gallons total. But if your calculator rounds the change to 100%, then what just happened? If your calculator does this artificial, well, not artificial. If your calculator rounds it off, then we're going to say all 100 gallons went to the left. Does that sound right? No, and that's called a round-off error. Right? Not all 100 gallons went to the left because there's still a little bit of water on the right. But depending on your calculator, how many digits it carries, it'll round that off. Well, instead of this is not good because we're going to have a big change. And we're worried about it. The only reason we're worried, I mean, you can approach equilibrium. It doesn't matter where you approach equilibrium. You can approach it from the right or you can approach it from the left. It's just the problem is with the calculator. And a lot of people will say, I have a very fancy, expensive calculator, but I can always choose the numbers, right, to defeat your calculator. And so you have to learn this technique. Versus if we approach it from the if we approach it from the other side, then what's the change going to be like? The change is going to be much smaller, and thus we aren't going to have any issues because your calculator can do very small numbers, right? Like 7 times 10 to the minus 9, 7 times 10 to the minus 10, no big deal, right? In fact, you could have 8 digits, 7.0000 times 10 to the minus. And so do you guys see the point of resetting? Because the thing is, we aren't getting rid of water. We're just moving all the water to one side or to the other side. Well, the concept is the same in equilibrium. We aren't getting rid of atoms. We're just moving all the atoms to the right side or all the atoms to the left side, depending on where we want, where we see most of the atoms. Where should most of the atoms be in this equilibrium? Most of the atoms should be on the left side, so we'll just push all the atoms, convert these atoms into N2O4 and just push all the atoms to the left side so that the change becomes a little, well, the change is actually small because it's close to equilibrium. And so the purpose of this is not to minimize the change. The purpose of this reset would be to bring the initial conditions closer to maybe the equilibrium conditions. Does that make sense? And so in this case, if I were to reset this, I perturbed it. I perturbed it here. So I could go ahead and do the perturbed conditions, or I could just reset everything. And so when I deal with the perturbed conditions, it's like this. I shouldn't have erased it. But when I deal with the perturbed conditions, I can do the calculation like this. I just redo my initial conditions. My initial conditions will be here now, right? So I redo the initial conditions and then just calculate the change. It's going to drop from the perturbed, it's going to increase from the original, and this should increase from the original, since we only perturbed this side. Does that make sense? This one we perturbed both sides, but we could figure it out. That's one way, or I could just perturb it like this and then just reset all of it. That might make the calculation easier. And that's what I'm going to do. I'm going to do a reset on this. So rather than do the change here and calculate it, I'll just reset the initial. And I'm going to move all the atoms to the left. And so when I move all the atoms to the left, this is going to be plus, I'm going to call it y now, rather than x. And this is going to be minus 2y, where minus 2y is all the atoms. So I'm going to just go ahead and do this. It's based on the LR. So here, the minus 2y will be 0.01933 molar. And so plus y must be half of that, which is 0.01933. And so my new initial, actually just reset, will be what? Oh wait. Just go ahead and add it. What is this? 0.00?
965.
965? 665. We're allowed 3 sig figs. And so we'll add that to this. So that's going to be 0.3332 3332. 0.3332 molar. Is that right? All right, and this will be 0 molar. And so what I've done is essentially done this, just pushed all the water to the left. Here I'm just pushing all the atoms to the left because these are two-way reactions. So it's going to react. Some of the atoms are going to shift to the right. And so the change now is going to be in which direction? Change is going to be to the right, to the side of the 0. So this is going to be minus x molar plus 2x molar. And so at equilibrium, I'm going to have 0.3332 minus x molar and 2x molar. And so now I'll solve for x. Plugging in Kc. Kc was the NO2 concentration squared divided by the N2O4 concentration at equilibrium. So this is going to be 2x quantity squared divided by 0.3332 minus x. And then we'll get it into quadratic form. This is going to be 4x squared. And then minus 4.6. Actually, no, I got it mixed up here. 4x squared plus 4.61 times 10 to the minus 3x. And what's 0.332 times 4.61 times 10 to the minus 3? A question?
Yeah, did you choose to reset everything to the reactant side because Kc favors the reactant?
Yes. Okay.
I was just wondering, is the idea that increasing volume favors the products because it has more moles irrelevant because the Kc value tells you that it favors the reactant?
No, that's not irrelevant. You know, increasing the volume is different. Increasing the volumes for Le Chatelier's principle. So once we have the equilibrium established, the actual equilibrium is going to favor the reactants. But if we perturb that equilibrium by expanding the volume, then it will favor the product. But favor the product just means it shifts and forms more product. It doesn't mean all of a sudden the products become favored. It just means that that's going to be the direction, and we'll get a little bit more product, but not much. And so the equilibrium still favors the reactant, regardless of what the volume is. It's always going to be biased towards the reactants. It's just how it changes when you increase or decrease the volume. That's all. These are very minor changes. This is Le Chatelier's perturbation. It can be significant depending on what you do with it. But did someone calculate this? 4.61 times 10 minus 3 times 0.3332? 0.001 536. Like I say, I normally just carry one extra digit because that normally minimizes the round-off error and makes you think less. You know, by carrying these extra digits now, you save time later when you do your double check, because if your double check is right on the K, then you can move on to the next problem. But if your double check is off, like 49.1 versus 51.2, then you waste a lot of time thinking, did I make a mistake? You know? And so carrying these extra digits is helpful. This is equal to 0. Also, getting that calculator is very helpful. Min mentioned that she was able to pick it up off Amazon for what, $9?
Tax was
14?
14.
Okay, 14.
I ordered it yesterday.
Hmm?
I ordered it yesterday.
You ordered it yesterday? And so does somebody have a calculator that can just punch this out for me? Unfortunately, you can't use your TIs for this class. But you can't use them for standardized tests anyway. And a lot of you are going to be taking standardized tests later on. And so you might as well get used to using a regular calc. It's always good to have a backup calculator too, in case you're programmable isn't working. Someone have it? 0.0? 0.01 1902. Okay, here we have 3 sig figs. We're allowed 3 sig figs, so we'll just leave it. 0.01902. Is the change very big? Is the change very big? No, not very big. And so let's go ahead and do the calculation. 0.3332 minus 0.01902. So it looks like we're allowed 3 decimal places. So this is going to be sub 2, 2, 5, 3, 0.3. Oops, I'm supposed to subtract. Sorry, not half. So this is going to be 8, sub 8. 1, 12, 3, 1, 3. 0.31318, all right, molar. And this will be just 2 times that, which will be 0.03404. Wait, 9 times 2, 38. 04. Is that right? All right, now this is why we carry these extra digits. We carry the extra digits when we do the double check. So let's see. What does it come out to? 0.03804 squared divided by 0.313. You know, since
314.
31418.
31418. Okay. 31418. I might as well carry that to avoid, you know, because the more round off, the more uncertainty that adds to it. And so, we aren't allowed those, so we get rid of them at the end, but we're only going to get rid of them at the very end, right? Best is just carry all the digits, but you know that becomes a hassle, especially on long calculations. And so, what does it come out to?
0.0046.
0.004606. And so, when I look at it, it's supposed to be 461, it's 460.6. So, is that pretty good? Yeah, that's pretty good. Here we wouldn't be concerned. It looks good. Our double check and our accepted value K are the same. Round. All right, they're probably asking for the mount, the moles. You know, so we'd have to do an extra step. We'd have to multiply by the initial volume or the perturbed volume? perturbed volume, these are the concentrations in the 3 liters versus the 0.75 liters that we had initially.
What number, what problem?
What problem is this? A good question.
Is that it, like,
What number problem was this? 40? Number 40? Thanks. Number 40. And so I think, did they ask for the amounts in number 40? I'm going to pull it up. You know what, when I do these calculations up on the board, do you guys repeat them at home to make sure the answers are, yeah, you need to do these as well. I might have made a mistake, you know. You want to check them. And also make sure that you can do them yourself. It's very important. Because watching somebody do it, what is the composition? So I guess, well, the composition, we just have to figure out the moles, since they probably want the moles. So we just take this and multiply by 3 liters. 3 liters is going to be to how many sig figs? 3 sig figs.
so we adjust every time we make any changes that affect the equilibrium? Is that what we...
Yeah, you know what we do? This is very common, this Le Chatelier's, but this is not a common setup in this particular problem. We have another common setup, and that is with water. This is in the next chapter. We do reset all the time. All the time. We reset it. Because it's just easier. You know, for example, in water, do you know what the pH of water is supposed to be? 7. And the pH is the hydrogen ion concentration. But when you add acid, you know, that's an equilibrium. And when you add acid, you perturb water's equilibrium. And so there are 2 approaches. One, you could get the perturbed initial, and so water goes from 10 to the minus 7 molar, which is pH 7, up to whatever, and then work at it. Or you just reset it. And the easiest thing to do with water, I mean, we're going to get the hydrogen ion concentration later anyway. If we add acid, we'll just reset it to 0 and then go from there. It's a lot easier. And so we reset. This is not an uncommon technique, even though it's not discussed in this chapter. They do it in the homework, right? And so it's a very, very common technique to reset the equilibrium. And not only that, in this chapter, if you do not reset some of these problems, you will not get the answer because your calculator is going to round it off and give you a 100% change. And then when we calculate our K, and there's a 0 in here because you've just consumed or produced, you know, 100% one way or the other. If there's a 0 in here, then K, your calculated K is going to be either 0 or infinity. And so if your calculated K comes out as infinity and your K is supposed to be 52.1, how good is that of an answer? It just doesn't work, right? And so in this chapter, in the advanced problems, you have to reset. Otherwise, you aren't going to solve the problem. Okay. In this problem, we didn't You know, you don't, but just resetting just makes less work. That's all. Did you have a question?
You solve for y right there. You divided by 2.
Well, y we're just okay. When I solve for y here, this is when you reset, you assume 100% forward or 100% reverse reaction. And so when I did this, I just assumed 100% reverse reaction.
Okay.
In other words, I'm pushing all the atoms to the left. So 100% reverse reaction, then, you know, you look what the limiting reagent is over here, and then you consume all the limiting reagent. We only have one reagent, and then push it backwards. Sometimes we have multiple reagents here, and so we got to look for what is the limiting reagent. And we can only reset, consume all that down to 0, and then we'll have excess reagent left over here. That happens frequently, too.
So you just take the initial that you get for the limiting reagent and you make that y. Always.
Well, it depends on the ratio here.
Okay.
You see, this is 2, so it's got to be 2y.
Oh, I see. Okay.
How the ratio that they react in other words, the stoichiometric coefficients. So let me take a look at the next problem I need to do here. Forgot to write these numbers down. Let me write them.
Because you're moving it all to the left side.
We're going to take a look at '47 next. Actually, let's skip 47 for right now, sorry. We're going to go to 44. All right, if we look at 44, lead metal is added to 0.100 molar chromium-3 aqueous. What are the lead-2, chromium-3, chromium-2, chromium-3 concentrations when equilibrium is established in the reaction? All right, well, talking about this resetting here, if you look at the previous problem, look at the Kc value here, 0.288. Does it really favor one side or the other? No. And so in this case, you know, resetting it to the left, resetting it to the right, doesn't really make any difference. The only reason you might reset this is to get more zeros. The more zeros you have, the fewer.
Is that for 43, that value?
Yeah, this is the value for 43. Just comparing. Versus this value for 44. Take a look at the value for 44. 10 to the minus 10, which tells me it's all reactant. 10 to the minus 10.
So we reset for that.
Well, it depends. We would reset this if we were just given products and zero reactants. As if we were given all products and zero reactants, then the reaction should proceed to the left, and the changes are going to be big. Like 99.999999%, which your calculator would probably round off to 100% change, right?
How do you know, like, when we put reset or not?
No, we have to look at the ICE table to determine that. And so, we will look at the ICE table to determine that.
I thought you have to do the
then we look at it. Does it look like we want to reset or not? And so, I'll show you an example of where we reset it. Well, let's see if we want to reset this one or just leave it alone.
44?
Yeah, this will be number 44. Black pen. So here's the reaction. Lead plus 2 chromium, lead solid plus 2 chromium 3 plus goes to lead 2 plus 2 chromium 2 plus. This is a redox reaction. Chromium 3 is the oxidizer, lead's the reducer. Chromium 3 must be a much stronger oxidizer than, what's the oxidizer on the right? Lead 2. It's got to be a lot stronger. Over here, chromium 3 is the oxidizer, but is chromium 3 a lot stronger oxidizer than, what's the oxidizer on the right? Cadmium 2. Take a look. Look at the K, and what does that tell you? Which one are we going to get more reaction? Both of these have chromium 3 as the oxidizer. That means it just must be a lot harder to oxidize what? Than what? It looks like it's just a lot harder to oxidize lead, right? Because very little reaction takes place. And cadmium must be a lot easier to oxidize. Since cadmium is a lot easier to oxidize, we call it a better reducing agent than lead. Well, anyway, going to this, let's just see what we have. We have 0.100 molar chromium 3. What do we do with solids? One. And so does the activity of the solid change? No, so it's pretty much the same. So we just do a line like this.
Oh, we don't put 1? We
don't put 1. We'll just leave it blank. Chromium 3 plus, 0.100. Lead 2, 0. Chromium 3, 0. Well, I mean chromium 2, 0, sorry. And so here, should we reset this, or does this look good? We don't want to reset this one because it should be mostly reactant. It is mostly reactant. If we were to reset this, it wouldn't make sense. Let me just do that just to show you. If we reset this, then we do minus 2y plus y plus y. We look, what's the limiting reagent? Well, there's only one reagent here. We have to assume we have excess lead or enough lead to establish the equilibrium. If we didn't have any lead, obviously this reaction wouldn't occur. And so we're just assuming we got plenty of lead. And so chromium 3 should be the limiting reagent, and what's the reset initial going to be? Well, if this is limiting, we should lose all of it. Therefore, y must be 0.05 molar. Okay, now does this look like a good set of initial conditions? This looks like a poor set of initial conditions because, the change is going to be huge. And so, let's say the change were 0.04999999999. What would your calculator round that to? Your calculator would round it to 0.0500 and 0.0500, right? And you'd end up with 0 and 0. And then when you double check your calculation, you see your K, calculated K, is going to be 0. Is 0 the same thing as 3.2 times 10 to the minus 10? Not even close, right? And so, sometimes they'll throw problems like this at you to see, can you handle this? Or maybe they try to keep things nice. If they try to keep things nice, they'll only throw problems like this at you. in which you just follow the standard procedure. But we aren't going to reset because this looks good. And so we know that the change is going to be minus 2x plus x molar.
Plus 2x? For chromium 2?
Oh, plus 2x, sorry. Then I screwed up. This was plus 2y. This should have been 0.100. Sorry. And so at equilibrium, I'm going to have 0.100 minus 2x molar, x molar, and 2x molar. So let's solve for x. I should have written that down. It's something times 10 to the minus 10. Was it 3.2? 3.2 times 10 to the minus 10. So the Kc is going to equal the lead-2 concentration, the chromium-2 squared, divided by the chromium-3 squared. Okay, let's go ahead and plug that in. We're going to get x, 2x quantity squared, divided by 0.100 minus 2x squared.
So we ignore the lead solid?
Yes, the lead solid is in here, 1. Activity is 1. This is equal to 3.2 times 10 to the minus 10, the given value for Kc. And so this is going to be what, 4x cubed divided by, let's go ahead and multiply out this binomial. We're going to get 4x squared minus 0.2 gives me minus 0.400x. And 0.1 times 0.1 will give me plus 0.0100. Correct?
Equals
3.2 times 10 to the minus 10. Do you guys, without the fancy calculator, know how to solve for cubic equations? You know the Casio FX115ES will do cubic equations too. And so you just get this into cubic form, and you plug in A, B, C, D, versus quadratic where you plug in A, B, C, right? And so you could get this into cubic form. You have two choices here. Get it into, the cubic, the ax cubed plus bx squared plus cx plus d is equal to 0, and then use your calculator, your non-programmable calculator. But, but there's an alternative way you could solve this without buying that calculator. Because I can't force everybody to buy the calculator, right? And so, how do you do a cubic? How do you guys solve cubic equations in algebra?
You break it into a single technique. I'm not explaining that.
You guys graph?
Quadratic and then you make it.
You guys graph? No?
You can draw.
Oh.
Yeah, you would
What's the name of the calculator?
Well, no, forget about the calculator, because the Casio FX115ES only goes up to cubic. But if it only goes up to cubic, then I'm going to have to put a higher order problem on there. Otherwise, you can solve everything with a calculator, which I don't want. And in fact, the next problem we're going to do, you can't use the Casio FX115ES to do it. And so, you know, or we just solve it from here. Or we use the method of successive approximation. All right, so how many of you have not used the method of successive approximations? You never used it? The method of successive approximations is just a fancy method of the, fancy name for guess and check method. So it's a guess and check method.
So why can't we use the calculator? Oh, to do the math.
Do you remember the guess and check method? You just guess a value of x. But, you know, what is our first value of x going to be? Our first value of x that we're going to guess, well, x is limited. X has to be between 0 and 0.05. Otherwise, we get a negative. So we just pick a number between 0 and 0.05. That's one way to do it, right? And then it takes time. But, you know, is that it for my... Are there any other tricks I might be able to use to make my life easier? Are there any other things to make the math easier that I could do right now? See, so I either buy the calculator, this is like 20 bucks, or I use the method of successive approximations, which is free. It just takes time. It's easy. It's not that difficult. But is there anything else I might try?
Oh, I know.
You know.
Simplifier.
Yeah, you know what? I didn't even try something. I should have tried something else before getting this far. I should have tried the simplifying SA, which is called the, or I could try the SA, you know?
What's the A?
Assumption. So I have some choices here. Why not just, you know, do I expect x to be very big? No, 2x is the change. Do I expect 2x to be very big? You know, how much forward reaction do I expect with something like this? Yeah. Oops, actually, not much, right? Not much. And so, you know what? I think the simplifying assumption is a pretty good candidate for this problem. And in fact, I would just try it right out. And so if I use the simplifying assumption, I'd say that Kc is, will this x go to 0?
No.
Would this x go to 0? No. How about this 2x? We're going to assume that the 2x is so small compared to 0.100 that it'll have negligible impact. And so when we do the simplifying assumption, we're going to just say that Kc should be approximately to x times 2x quantity squared divided by 0.100, assuming that 0.100 minus x, we assume that 0.100 minus x is about equal to 0.100. And so 0.100 is like an Olympic-sized swimming pool, and you just take one drop of water out of that. Is it going to be any impact? No, but how do you know how big the drop of water you're taking out? And so we have the, you know, that circular justification for this, right?
You still have to square the bottom.
Yeah, we still have to square the bottom. Now take a look at this.
4x cubed.
Can you do this with a cheap calculator, the $8 calculator that you probably, a lot of you have? $9 calculator? Yeah, because this is just going to be 4 x cubed divided by 0.0100 is equal to 3.2 times 10 to the minus 10. Well, a lot of people, I don't know. Every semester I get a group of people who absolutely refuse to do the simplifying assumption because they think, it's not right. It's not proper. It's not math. This is the wrong answer you're getting. And it's true, we are calculating the wrong answer, but hopefully it's not that wrong. But the problem is you aren't going to get very far in science because, things get so complicated that you start to have to make a lot of assumptions. And the thing is, you have to get a gauge of how good your assumptions are. In this particular problem, I think my assumption is going to be very good because that k is so small. And so anyway, what does x come out to?
There we can use the...
You just do the cube root. So 3.2 times 10 minus 10 times 0.01 divided by 4, cube root of that. Okay, we're allowed 2 sig figs, so 2.00 times 10 to the negative 3? Yeah. 2.00 times 10 to the negative 3.
Go with no 3, like.
Huh?
Not 3? Negative 3. No, that's wrong.
I got 0.00009.
0.00009. 4 zeros and a 9.
4 zeros, 9,
and
then 2 8.
2 8. Okay.
3.
All right.
How many? Well, only 2.
We're only allowed 2,
Yeah,
so
so
I
9.
carried 1. But sometimes you'll carry more. We'll just carry 1 and see. Is this what other people got?
But that's 2 times 10 to the negative 4.
I'm going to repeat it.
That's right.
I'm pretty sure I'm right.
Oh, you got that? Oh, it looks like most people got this, so we'll go with this.
Yeah, that's right.
All right, now how do we justify this? Simplifying assumptions. What do we do to justify? Yeah. Check if the calculated change is less than 1.5%. And so we need to calculate the percent change. The percent change is equal to the change is equal to the change over the initial times 100%. And so the change here is going to be 2x, right? And the initial is 0.100 times 100%. And so 2x is going to be double that, which is going to be 0.0001856.
Wait, why is it 2x?
Because I made 0.100 minus 2x. And this comes out to what?
Yeah. 0.1856.
0.1856%.
Yes.
And so is that good?
Yeah.
Yeah, I wish it was better, but it's all right. So it's okay. How much time did we just save on the problem? A lot. We just saved a lot of time. And so now it's okay. It's less than 5%. We're going to move on here and go ahead and calculate this. So this is going to be 0.100 minus 0.0000185. Well, I'm trying to be consistent this semester. In past semesters, I carry extra, like 2 extras. This semester, I was going to get by with just carrying 1 extra digit. But maybe it's not enough. Maybe we need to carry 2 extra digits. Let's just try to carry 1 extra digit and see what happens. And so this is going to be 0.0998815. Here I'm carrying extra. X is point 0.quadruple 0928 molar, and then 2x is point 0.0001856. We'll just carry 1 extra. Maybe we should have carried it over there. We'll see. Let's calculate our K as a double check and see if we're even close to what it's supposed to be. So can someone calculate the K? Which would be quadruple 0928 times 0.0001856 squared divided by 0.099815 squared.
3.208.
3.208. 3.208. No, 2 sig figs. 3.208 times 10 to the negative 10. How does that look? Good. That looks great. And so we're good. Actually, you know, the percent reaction, what was the percent reaction? If I started off with 100, I lost 0.185. And so the percent reaction is only 0.18% reaction. Very little forward reaction, right? Very little forward reaction, but there was still some. We formed a little bit of product. Not much, you know, with only 0.185% reaction, 0.2% reaction. But that's what this K tells us, you know. In fact, 10 to the minus 10, what was the assumption that I gave you? 10 to the minus 10 and smaller is essentially no reaction, but, you know, a little bit of reaction took place, 0.2%. And so it depends on your perspective. You could call that no reaction, or you could call it a tiny bit of reaction. You know. Definitely some reaction took place. We'll take a break here.